Okay, so now, hi everyone, first of all. So today I think we will actually prove this thing that I promised first, so that this will be our first goal, to get the analysis basically worked out and out of the way in some sense. So we're going to prove this elliptic. Well, today we won't get it completely worked out. This aspect, finiteness and regularity, will be done today. But then there is still some more analysis needed that we'll do in next lecture. Maybe a couple of more lectures is needed to get the heat kernel expansion. So existence of heat kernel and asymptotic expansion for heat kernel. So that's the extra analysis, kind of geometric analysis we need. But this is, no matter what, is needed. Okay, so so as I said, we have most of the elements in place now. So what we need to do, we have to lift all this Sobolev theory and pseudodifferential calculus to manifolds, and just use the local regularity theorem we proved for Rn, and use Rayleigh's lemma, Sobolev lemma, and these things to get things that we want to do. So the first step is to move up to manifolds, everything. So for that, let's assume M is a compact manifold. So compact, I really mean closed, means, yeah, without boundary. So is a closed manifold. So yes, I think E and F vector bundles over M. So the first thing is to understand what pseudodifferential operators means in this context. So my notation, I believe, is P from C infinity of E to C infinity of F. C linear map. So this C linear map is called a pseudodifferential operator. Pseudo. If we go to any local charts and local frames for E and F, we get an operator which is a pseudodifferential operator. So if it is, P is a pseudo, if it is a pseudo locally. So what does this mean? It means that i.e. for any coordinate chart, say U inside M, open in M, and any local framings, local frames for E and F, map that we get by reducing this to this open set and local frames, P from C infinity of U cross, say, RP to C infinity of U cross, maybe I should say CP cross CQ, say with compact support with compact support. Yeah, is a pseudo. So maybe I just put here V. Just put here V. So there is this phi that takes you inside M to V in Rn. So what we can do, we can just use this coordinate system to write a map on transfer maps, transfer functions or sections on U to sections on V. And using framings, we get trivial bundles like that. And then the corresponding operator should be is a pseudo. So these pseudos, which are kind of vector valued pseudos, what does it mean? It means that it's a matrix, is a Q by P matrix of pseudo-differential operators, scalar pseudo-differential operators. So IE is a Q by P matrix of pseudos. Okay. Now, technically, you may complain at one place about the formality here. And the issue is that you might say you just define your operator from C infinity of E to C infinity of F. How can I look at the things on here? But I just said compact support. So if you have a function with compact support, you can extend it to the whole thing by 0. So you get global sections that way. So technically, P is really defined. And that's good. So the definition at least makes sense. And so that's the idea of basically to lift things from Rn to manifolds. So we did two generalizations. First of all, we went from Rn to manifolds, and also the theory that we developed was for scalar pseudos, but here we are dealing with vector valued pseudos, but it's not critical. So that's what we have right now. Yeah.
If we change coordinate systems,
so changing what? Yeah, coordinate systems. And what is clear?
Is it clear whether the definition of pseudo defined like this is inherent?
No, it's not clear. But I'm not using that. I'm saying in any coordinate chart, it is a pseudo.
If there exists a coordinate chart.
No, I didn't say if there exists. I said for any coordinate chart. If you want to show that there exists an open cover in which, then you have to show that if it is pseudo in that coordinate chart, then it is pseudo in any other. That's not clear. Yeah, that needs some.
But that is true.
But that's true. That's true. Yes. Yeah, that's. But I mean, formally, I don't need to use that result at least to prove this. But that result may be needed for something else, but not right now. Okay. So at one stage, we need the idea of pseudo of order n for any, say, real number. So let me give you an example. A pseudo of order n belonging to R. So what we can do, we can actually cover this M by open sets, by some open sets, maybe by finite number of open coordinate charts. And then on each one, so first of all, write union of finite cover by coordinate charts. And what we can do, we can define operators on these U alphas by fixing their symbols. So I'm going to choose the symbol to be 1 plus xc squared to the power m over 2. That's the kind of symbol that we used. So my notation that is consider symbols 1 plus absolute value c to the power m over 2 on V alpha. Again, V alpha is the corresponding open set in Rn. We just choose those symbols on the corresponding open sets here. Then P, which is equal to sum, I can just say rho alpha V alpha is a pseudo
Sorry, what is the vector quantity?
the pseudo of order m. It's a scalar pseudo, the way I defined it actually on m. So what rho alphas are? Rho alpha is a partition of unity subordinate to this cover U alpha, right? So rho alpha is a partition of unity subordinate to this guys. And what is this d alpha? This d alpha is the differential, is a pseudo-differential operator with this symbol. Because using Fourier transform on Rn, we can just write this on each V alpha open sets on Rn, and then we patch them together to define. So this basically, this sort of pseudos you can do by partition of unity and do local definitions, it works. I mean, morally, you can also take, but we don't have the full technology yet, but essentially we can take something like, if we know some more tools, we can actually take something like this.
Just to clarify, the bundle there is the trivial bundle.
1 plus delta, for example, to the power m over 2, where delta is Laplacian for some metric, for some g. I mean, we can take this if we know how to make sense of arbitrary powers. I mean, at least for even powers, this makes sense because this would be a differential operator, we know, and powers of differential operators is a differential operator. So at least for this makes sense, but we don't have to use that. We can just use this local construction. Sorry, what was the question?
Just to clarify, the bundle there is the trivial.
Yeah, the bundle here is trivial, but I mean, you can. So this is a scalar pseudo. At least we make sure that such a thing exists. Okay, so this is the idea of pseudo. Of course, I mean, differential operators we defined first day or maybe second lecture. I mean, differential operators between sections of one is not a problem. That's a little more technical, so but it's essential. Another thing is now we have to define these Sobolev spaces on smooth manifolds for sections of bundles, for example. Sobolev spaces for bundles. Yeah. So at least, I mean, first let me do it just for C infinity of n. First, just for C infinity of n. Okay. So what we can do, so the idea is this: we want to define this Hs of n. Basically, we want to define the S Sobolev norm on C infinity of M, and then complete it to get these Sobolev inverse spaces, right? So that's what we want to do. So we can do the following thing. We can just again choose a finite open cover. Okay, so U alpha is a finite open cover for by coordinate charts for M, and then we can define the following norm, and for any S belonging to R, let and F belonging to C infinity of M, let norm F say S, I would say maybe squared, yeah, let it be equal to some norm rho alpha F say squared S. Yeah, so over alpha. Well, again, this rho alpha is a partition of unity, P of U, subordinate to this open cover. And by this, we really mean the resulting function on this open subset of Rn. So I just don't burden the notation with composing back and forth and stuff like that. I just, because what happens is this, you have a function on n, right? If you multiply by this rho alpha, its support is in this coordinate chart. Then you use coordinates to go to Rn, and then use the Sobolev norm over there, square, and then sum those things. That's the definition makes sense, right? Okay, so, and then you can define this Ws to be completion of C infinity of n with respect to this norm. That's, at least you can do this. I mean, logically, there is no obstruction to do that, right? So here, that is one definition. So then Ws(n) by definition is completion of, I mean, Hilbert space completion of C infinity of M with respect to this normals, right?
This is dependent on the part.
Yes. The drawback, I mean, if you want, the drawback of this definition is that we made a lot of choices here. First of all, we chose an open cover for M, and then we chose a partition of unity also. It depends on these two choices. Yeah, but yeah, there is some. I believe eventually there will be some logical issues, but it can be settled. These logical issues, it can be settled, can be solved. But for now, at least that's the idea. Now, one thing that I should mention is that we can give a definition which is independent of choice of open cover and partition of unity, but depends on something else. It's not totally independent. I mean, this is not a totally God-given construction. You know, so anyhow, before doing that, let me just mention about for S equal to 0, remember we had this W0 of Rn, H0 of Rn, right? The zero Sobolev norm using Plancher's formula. This was isomorphic to, right, L2 of Rn, right? I mean, these two Hilbert spaces are really isomorphic. I mean, isometrically isomorphic, unitary equivalent Hilbert spaces. We can do the following thing for s equal to 0, which is similar to that. We fix a Riemannian metric on M. Fix a Riemannian metric G on M. And just to make life a bit easier for us, let's assume that M is also oriented. So assume you can get away with this hypothesis, but let's not worry about that. Assume M is oriented as well. Then you have this volume form. And then, so these two hypotheses, G, fixing the Riemannian metric, first of all. And assuming M is oriented, you get this volume form. So the volume form is square root of the determinant of G, dx1, with dxn. Again, this expression only exists in local coordinates, x1, xn, but is independent of choice of coordinates. So this is a differential n form, right? So this belongs to, this defines an n form. It's called volume form, Riemannian volume form. We can all, so this is in local coordinates, but globally I can define it by d volume G. And so we can define an L2 inner product on C infinity of M now, which is this one. So let's define L2 norm of F to be integral absolute value of F squared d volume G over M. Right? This is an M form, and this is a scalar function. You integrate it. This is a pointwise absolute value square. So, okay, and then you complete it, you get L2 of M. So from here, you get L2 of M. So at least for s equal to 0, if we fix a Riemannian metric, then we get this L2 of M. And as I said, in general, by fixing a differential operator of order n, we can show that these metrics are actually will be independent of the choice up to scale equivalence. So I will tell you what I mean exactly. But the idea now is that having fixed this, at least in this setting, the following statements will be true. Okay, so then the following holds. One, there is a version of relic lemma which is just perfect in this case. So this is relic lemma. So it says that for any s less than t, the embedding ht. What was my notation for this? Did I use ht of n in hs of n? Is compact. Remember, when we were doing this on Rn, we said that the sequence of functions should have compact support. But here, because the manifold is compact, that's really, you can show that that condition is always met. So this is okay. So this is relic lemma. It's fundamental. The second one is Sobolev lemma, Sobolev embedding. So the idea is that for any s bigger than n over 2, remember this n is dimension of the manifold. So we have that h, k plus s is inside ck of n. So for any k equal to 0, 1, 2. So as soon as you choose your integer k such that, so s should be bigger than half the dimension. And then if, so I put n here. So if it is in the Sobolev space high enough, then it's differentiable enough. Ck differentiable, Ck continuously. So this exactly follows from those local statements. So that's fundamental. And third one, of course, is this continuity statement that if P has order n, then it defines a continuous map well, yeah, okay, so I just denoted again by P from H Sm to H S minus M of that. Right? So that's the condition. So it defines a bounded map from this inverse space to that inverse space. Okay, so so that's these three lemmas are absolutely fundamental for what we're going to do. So now let me just mention that you can actually define Sobolev norms in an alternative way. So this is this proposition for any s bigger than or equal to 0, the norm, and for any, I would say, elliptic. So this is important. For any elliptic pseudo of order S, the norm so let's define this norm till S equal to norm F L2 plus norm P of F L2 is equivalent to this Sobolev norm. So this is, you can imagine, this is for any f belonging to C infinity of n, but very soon we are going to assume similar statement for sections, and also we are going to say that these are true also for the corresponding Hilbert spaces because it extends So, I mean, to put it formally, one should also say that for any local charts and for any partitions of unity, the norm that we define here, the Sobolev norm, is equivalent to this norm here that's just defined in terms of sums of L2 norm of F and L2 norm of P of F. And now, this depends on the metric, of course, because it's L2 norm. Also depends on the differential operator. It's also the differential operator, which is a pseudo of order S. So what is the point of this proposition? The point is that, yeah, I mean, this is equivalent. I mean, you can define these Sobolev norms using elliptic pseudos of order S with this formulation. And proof of this result, amazingly, is not so easy. I mean, it needs this regularity theorem that I proved last lecture. So we have to use something for the proof. Equivalent means that this is less than equal to some multiple of the other one and vice versa for some constant that just depends on, it works for all elements, for all F elements. Okay, any questions?
If we can define these Sobolev spaces either by differential operators or by a partition of unity and coordinate charge, but they're always equivalent, doesn't that somehow say that relative choices matter? You always get the same spaces? Because on one hand you can vary the operator, and on the other you can vary the coordinates, but they will always be equivalent to any choice.
They're always equivalent, right? But so, but the logical issue, I think, is that, yeah, I mean, we have to make sure our constructions does not depend on Hilbert structure, only depends on the Hilbert structure up to this equivalence. There is a little bit of subtlety still there. I mean, this doesn't quite settle the things. One can, I mean, okay, one can do a little more, namely, we can just fix a Riemannian metric, because we will see, the Riemannian metric we cannot get rid of, because to do harmonic theory, no matter what, we need Riemannian metric anyway. So fix a Riemannian metric. Then for this P, we have a more or less canonical choice, which is 1 plus Laplacian, the whole thing to the power S over 2, for example. That's really a pseudo of order S. And that's kind of canonical. So we can use that. But again, is it, so I have to think about it. I mean, there is something there that still bothers me. I'm not totally convinced that we don't need further arguments. So, yeah, so this Sobolev and pseudo theory over manifolds, one has to be a bit careful. So, but it has been worked out, and it's safe to use it, I guess. Anyhow, so yeah, that was a good question.
So,
yeah.
so did we define elliptic pseudo on manifolds?
Elliptic pseudo? No, I didn't define, but I'm saying if you can define the symbol of pseudo, then ellipticity means exactly like the original definition. Which
No,
would
so
be,
again you would say for all charts.
no, yes.
Ambiguity.
Yeah. Like that, and then you have to show that if it's even independent of coordinates. I mean, independence of coordinates comes somewhere else. For that definition, you don't need that. It's the transformation property to get the fact that symbol is a section of a certain bundle. You need that independence. You need that transformation property. Well, I will get to that thing. But for this stuff, you don't need independence. Okay, so that's what we want to prove. All right, so. Okay, so proof. Okay, choose, I just say, a parametrics Q for P. So PQ, I would say QP minus 1, that's asymptotically 0 or infinitely smoothing, and PQ minus I also. So what is this? I think I defined what parametrics means. That's pseudo inverse to this pseudo for the symbol of this P. Because since I can say something like this, since P is elliptic, or what we did in the last lecture, can choose a parametrics Q for P such that QP minus identity is infinitely smoothing, PQ minus identity is also infinitely smoothing. The way we did this, remember how we did it? We went to the symbol of the operator and solved the system of equations that we had to do in using product of the symbols, right? And then we solved that recursively. We can solve this using ellipticity. The first step can be worked out, and then step by step, we found this inverse symbol of the quasi-inverse or parametrics, and then you can do those things in each coordinate and patch them together, and then. So this exists. Okay. So then you can argue like this. So then a norm. Say U of S, maybe not F, because to be consistent with my notation, is less than or equal to, you just use triangle inequality. This is QP S plus norm QP minus identity. This is just triangle inequality, right? So this is less than equal to norm Q P of F S plus C times norm 0 of F. And the reason for this inequality, this is the crucial inequality. The reason for this is that this is an infinitely smoothing operator. So that embedding, remember, from HS to HS minus M is bounded. So this is since QP minus identity is infinitely smoothing. So its order essentially is minus infinity. So what does it do? It sends HS to HS minus M for all M, even negative. And then from this it follows that this inequality is true. You should think about it, right? So that's
C is some constant.
What's that?
C is some constant.
C is some constant. There exists a constant that just depends on this S, on the scale S, because S is fixed now. I'm just arguing with one S at a time. So now this is less than equal to some other constant C prime, norm of PF S plus C norm. So this is norm 0, sorry, plus C norm 0 of F. So this is because Q is an operator of order S. right? It's a pseudo, sorry, of order minus s. So this Q is a pseudo of order minus s. So we have this inequality, boundedness of the maps, and this one.
So C prime is essentially the operator norm of Q and
Yes.
maps from HS to H0.
Exactly. Right. Okay, so then this is then you can say this and this time equals C double prime, then norm 0 of F plus norm 0 of F. So one inequality, one direction is proved. But notice, I mean, this came at a huge price. I mean, not price. I mean, this result about the existence of parametrics is a very strong result. I mean, we had to, develop this pseudo-differential techniques. Okay, now the other inequality, conversely, that's actually easy. If you want to compare norm F2, which is 0 really, plus so we just say, okay, so maybe I'll just say like this. Norm P F0 is less than or equal to C times, again, some other constant. It doesn't have to do those other constants. C times norm S, right? So now this follows because P is a pseudo of order S, and this is the boundedness of that map, continuity of the map, right? Since P is a pseudo of S. Okay, so this is okay, so we can just write this less than or equal to that one, then we have this less than or equal to. So let me write it. Hence, norm F 0 plus norm 0 less than or equal to some constant C times norm Fs. Yes. Right. So why I can do that? Well, this is less than or equal to that, but you notice norm F0 is less than or equal to norm Fs itself, because S is positive. When you do this Sobolev norms, if you increase the S, norms increases. Look at just the Fourier transform definition. So then this is okay. So the equivalence of these two norms is okay. This is what might give us a little bit more comfort, but it's not total comfort yet. I think one has to introduce a little more concepts in order to feel completely comfortable. Maybe even the context of Hilbert spaces is not totally enough. Some new concept should be defined, some sort of Hilbert space up to scale or something. And then we have to do analysis, do the whole Sobolev, not the whole Fredholm theory in that context, but that's not very difficult. That's not very difficult. Yes?
This second inequality does not depend on plasticity at all.
This doesn't, no. This doesn't. Because it's just P is bounded. Yeah, just going from that HS to S0 is continuous. That's it. Right. Okay, so now we can do analogs of all of these things for sections of vector bundles. That's what we need. So we need to fix an extra piece of structure for vector bundles, namely a Hermitian method. So now let E over M so be a smooth, complex vector bundle over M. So we fix a Hermitian metric on E. Again, we have to choose a metric. There's no way it seems around this. And of course, as before, I'm assuming that M is closed, oriented, and also a Riemannian metric is fixed on it, right? So they are. Then you can define a space of L2 sections of this, okay? So then you get this norm, norm C L2 for any smooth section C of C infinity of E in the following way. You can just take this to be, you can integrate, you can fiber-wise take the inner product of CX with itself, right? You can take square maybe, fiber-wise inner product like that, and then you do d volume G of, I would say, X maybe. You integrate over. Okay. So we are doing fiber-wise norming, and then multiply. You get a scalar function on it, and then you multiply with this volume function. So this is an inner product, and that's a Hilbert space. And then you complete it, you get L2 sections. From here, you get, as I said, L2 sections of E. So I denote it by L2 of E. So that's space of L2 sections of E. That's one Hilbert space, that's important. We can also define a space, Sobolev space of sections of order S by a similar method. Again, also define HS of E Sobolev the S Sobolev space of sections. Again, we can choose a partition of unity subordinate to a coordinate chart cover and framings and all those things we can do, and then so we get these things, and all those results go true actually. So relic lemma, Sobolev embedding, or Sobolev lemma. And that continuity statement are true. Also, a result similar to what we just proved here also holds, namely, these S-Sobolev spaces can be defined in terms of one pseudo-differential operator acting on sections of this guy, elliptic pseudo acting on sections of this, which you can construct of order S. Then you can define everything in terms of this kind of norm I forgot what's the. I guess there must be a special name for these norms, but I'm not sure. And this inequality, one direction that was difficult, I think it's guarding inequality, but I'm not 100% sure. Maybe it's just guarding inequality, but I'm not 100% sure. Okay, anyhow, but it doesn't matter for us. It just, so basically we have the analysis essentially out of our way, so to speak. Well, some further work is needed, but we don't want to spend all our time just doing these small fixings of analytic aspects. Now, the first goal now is to go and prove this finiteness and regularity for elliptic complexes and Hodge decomposition for elliptic complexes. Any question? Jeremy, do you have a question? At home? Good. Very good. So let's start. So assume we have an elliptic complex. So okay, so this is finiteness and regularity for elliptic complexes. So assume you have an elliptic complex. You remember, you know, we had even a tutorial on elliptic complexes. You remember elliptic complex is a gadget like this. You have a sequence of vector bundles, right? And differential operators acting on sections. Maybe K 0 and coming from 0. And then generically, I denote these differential the operators by D. I mean, D is a differential operator, even pseudo-differential operator of any order you can imagine. It doesn't matter. I just generically denote that. So assume that D is elliptic. Assume, not D. I mean, so I'm going to call this E, the whole complex. Let's call it E. Let's call this complex E. So assume E is an elliptic complex. So remember, what did elliptic means? Elliptic meant that the symbol complex is exact, i.e. The symbol complex is exact, i.e. for any x belonging to M, for any C belonging to T star M x, the symbol complex so the symbol complex now goes from fiber of E0 at x, fiber of this at x. So these are symbols. I don't know. I just denoted by x and c. Remember, and so on. So this is an exact sequence of vector spaces, and these are finite dimensional vector spaces. But that was the definition of elliptic complex.
Was it the symbol or principal symbol?
Sorry? Oh, principal symbol. Yes. Principal symbol, right. So let me emphasize, indeed, that's a good point, principal. So I just write with the poor notation, sigma principal, because we use two different notations, so you're aware of that. So One of the things is now we can equip these bundles with Hermitian metric, and we can equip M with a Riemannian metric. So equip EIs, I would say, with Hermitian metrics. You can always do that. And we equip M with a Riemannian metric. That's crucial now. And again, let's assume that M is oriented. So we are just assuming that M is oriented, just to make life a little bit easier. Okay, then it's not difficult to see that in this case, then there exists operators. Actually, if these are differential operators, these stars are going to be differential operators again. Right? Then there exist differential operators. This star going from C infinity of EI to C infinity of I minus 1, C infinity of in the other direction, which are formally adjoints of D. These are formal adjoints at least. Okay. Again, I don't write the i's, but you understand that at each I they work. So the formal adjoint means that, well, if you just take corresponding sections B phi and psi is equal to phi is star of psi. Now, to prove this statement, you have to be careful because we cannot use Hilbert space theory to prove this, right? Because this operator D from L2 to L2 is not bounded. So we cannot just take the adjoint of it. It doesn't exist from L2 to L2. But you don't need Sobolev space theory either. You can just work on the level of, so let me be more precise. For any phi and psi belonging to C infinity of EIs, or EI plus 1, etc. You can just work on this level and prove this statement. For this, then of course, I mean, this inner product uses this Hermitian structure, uses the volume. So you have to write down an expression for the adjoint that works. I mean, that's, I wrote down an expression on Rn. I believe a similar idea works in this case, but one has to be careful, no matter what this is. So I'm just telling you that one cannot just cite some abstract theory to get the existence of this star. And also it's very important to realize that this star is actually a differential operator again. Using, if you can do some abstract theory, this doesn't guarantee this star is abstract. I mean, doesn't give you a proof that this star is differential. So one has to be aware of this issue, but this can be handled. That's not a problem. Okay, so there is this. Now, what we can do now is the following. So we want to define now Laplacians for this. Okay, so using these stars, which are uniquely defined. So this is important. Uniquely defined. Of course, fixing Hermitian metrics and volume form from Hermitian metrics plus volume form, I mean plus Riemannian metric. Then we can construct a Laplacian. Okay, construct Laplacian. Laplacians, I mean, okay, so Laplacians in this very generalized sense we are talking about, right? So delta I, which I just write it like this, d star plus d star d. These guys now go from C infinity of ei to itself. Yeah. So, I mean, it's clear, right? So this is d plus d star squared, because, well, this is a complex. D squared is 0. You see, d squared is equal to 0. In fact, implies that its adjoint is also squared to 0. So this is equal to that, holds. That's fine. And okay, so all right. Okay. So now, what we want to do? We want to first of all, we want to make sure that these Laplacians are elliptic operators. So this is lemma 1. Delta I from C infinity of ei to C infinity of ei, right? Or maybe I should put ei up there, sorry. Is an elliptic operator. In the sense that its symbol is non-zero if C is non-zero, i.e. principal symbol of delta I at xc going from ei x to ei x is invertible matrix for every c different from 0 in the cotangent bundle of cotangent space at x and for all x. It's ellipticity, right? So what is this symbol now? I mean, principal symbol, we know that it's multiplicative, right? So we are talking about now symbol of this d star plus d star d, right? So this is symbol of d. I mean, let me put it like this, symbol of d star plus symbol of d star, symbol of d. Because symbol, leading symbol is multiplicative. When you multiply two differential operators, the leading part of the symbol of this new differential operator is product of the leading parts. So the leading parts don't they follow multiplicity. Is multiplicative. Some leading parts start to change what is. Okay, so now what we have to make sure that this operator now from ei. Okay, so from ei is invertible. Again, for all C different from C. And of course, this is not so obvious. I mean, mean, why? Because all we know is that this operator D, I mean, these symbols are, I mean, they form an exact sequence. And why, if we do this move, this is going to be, these operators are inverted. Any questions, maybe, before I give my...
Sorry, I had a very stupid question. Your notation for C infinity is your space of sections of physical.
C infinity of EI?
Yeah.
Yeah, it's a space of a smooth section. I mean, some people put M and EI, so I'm just making all symbols, all notations so much more kind of down to earth and at the expense of maybe sometimes creating confusion, I believe, but I hope at this, the ease of notation helps understanding better. Okay, so now actually this is a very good point for me to prove this in a general context. So first of all, let me tell you that this statement is pure linear algebra. It's just a finite dimensional statement. It's linear algebra, and it's a very interesting linear algebra. And the thing is, it's actually a finite dimensional version of Hodge decomposition theorem itself. So I'm going to do it in a way that you will see even what Hodge decomposition is in the context of linear algebra. What does it say? And you can prove it. You can go and prove, and then you appreciate the general result much more. Also, we prove this as well as a corollary. So I'm going now to take a detour into linear algebra to prove this, and then to give you an idea of Hodge decomposition better. So linear algebra detour, if you want. So we need a little bit of excursion into linear algebra. So the setting is like this. Imagine you have a complex of complex vector spaces. So let E be the following thing: we have 0, 0, V1, V n over k, 0. And allow me to use notation D, although it's a bit kind of in conflict with my previous notation, but just allow me to use this notation. So, okay, so this is so VIs are finite dimensional complex vector spaces. D squared is 0, so this is a complex, right? And we can take its cohomology, of course, right? What I want to do now. So now what we are going to do is this: put metrics on, equip the I's with Hermitian metrics. So once you put Hermitian metrics on VRs, then you can take the adjoints of these D's, right? But that's just finite dimensional, and that's straightforward. Let D star from VI to VI minus 1. This is the adjoint, in the sense of linear algebra. Everything is finite dimensional. Okay, so again, I just denote by delta to be, so delta I maybe, but it's really delta. Let D plus D star squared, which is dB star plus D star. Okay. So now I want you to, so here is a nice exercise of linear algebra which goes to the heart of the matter. So the first part is I want you to prove that there is a Hodge decomposition theorem for this context. So I call this baby Hodge decomposition because the level of difficulty of proving this compared to the Hodge decomposition we are going to do is like from 0 to infinity. I mean, there's an infinite energy level. But the idea is very, very similar. Baby Hodge decomposition. Which is the following thing. Vi, so let me put it like this. Vi is equal to actually kernel of delta I x sum image of D x sum image of this. This is an orthogonal Dx sum decomposition. Okay. I mean, everything is finite dimensional. That's why it's baby Hodge, but that's okay. And second statement is that the natural map. Okay, so I want you also to notice also kernel of delta is equal to kernel of D intersection kernel of D star. Kernel of D star. Now, part 2 of the exercise is to show that the map from kernel of delta to kernel of D induces an isomorphism from kernel of D delta to, so you have to go to quotient there. Kernel of D to image of D. And remember, this is of course isomorphic, so I put delta I, this is isomorphic to Hi of E. So this is the ith cohomology of E, right? Ith cohomology. Okay. So this is space, kernel of delta I, are called harmonic elements, harmonic functions, harmonic sections. So these are, let me call it harmonic I cochains in this case, because it's a cochain complex or something like that. I cochains. But this is ith cohomology group, kernel of D divided by image. So we will say that, okay, every cohomology class, every element, every cohomology class here has a unique harmonic representative. Okay. And if you prove these two things, then you can also immediately show that if the complex is acyclic, then this delta is going to be I mean, yeah, this delta is going to be an isomorphism, actually. So let me write it here. So can I erase this part? So the third part of this statement. So this is really a corollary of 2, is that if, so this was E. If E is acyclic or exact, so this just means that Hi of E is equal to 0 for all I, right? Then delta I from VI to VI is an isomorphism. I mean,
Kernel is 0.
its kernel is 0, so being injective is not a problem. So, but then this is going from a space of finite dimension to itself. So that follows from the statement. So this easily follows if you do one. But I highly recommend you do this and get this machine under your belt. That's very useful. Okay. Any questions about this? So 2 comments. What we are going to do is we are going to prove analog of this result for these infinite dimensional vector spaces, essentially. But this is not easy at all because nothing is bounded a priori. I mean, we have to prove all these results. But this is essentially what we're doing. That was comment 1. But comment 2 is immediate use of this linear algebra result. It immediately shows that this elliptic complex, for elliptic complex, is the differential operator delta I is elliptic. So this is another corollary. So assignment is done. So corollary of above assignment. So the corollary is that, in fact, in the elliptic complex context, complex case, these operators, the Laplacian, the generalized Laplacians, are in fact elliptic. Delta i's. So symbol of delta I at x and c is invertible. All c different from 0, right? So in other words, these operators are elliptic. So, this detour had 2 purposes. First of all, introduce basic ideas of Hodge theory, Hodge decomposition. And second of all, it also helped us to actually establish that this Laplacian, generalized Laplacian that we want is indeed is an elliptic operator. Okay, so now I can start. Now I can actually state what I wanted to prove. Any questions or comments?
So why is this a corollary?
Yeah, why is it? Anyone can answer?
Yeah, I believe if you look at the symbol for delta I, in terms of the symbols for B and B star, you're exactly in the situation of the exercise.
Right, but then you will show that delta is invertible.
Sigma delta, the symbol delta.
Yeah,
So
so
it's
you would have to show.
Oh, the notation is a bit, maybe you're confused by the notation. You see, the symbol of delta i's from the elliptic complex is what I call delta I in the linear algebra context. You see, for an elliptic complex, the symbol sequence is exact. So on the symbol level, there is no cohomology. So that's why we can use this linear algebra result. Okay. Yeah, so now I can state the result, main result, and prove it. So theorem, so maybe call it finiteness and regularity, maybe something like that. So, finiteness and regularity. Elliptic complexes. Oh, actually, before doing that, I want to do it for just I believe. No, I don't want to do it for. I don't want to. No, not yet. I have to prove something first. So theorem is this. So let's assume from C infinity of E to C infinity of E. So that's the kind of prototype of those Laplace type self-adjoint operators first we deal. Be a self-adjoint elliptic operator. So self-adjoint and elliptic. Operator of order, say, I believe this works for pseudo-differential operators. Let me say order and positive in that case. Then space L2 of E has a orthogonal decomposition, which is kernel of D, direct sum image of E, with kernel of D actually consisting purely of smooth functions. And kernel of D is finite dimensional. Okay. So to think about this statement, one has to be a bit careful. You see, this is in L2. I wrote my operator going from C infinity of E to C infinity of E. If you take it at face value, like from C infinity of E to C infinity of E, nothing like this could be true because L2 of E is way too bigger than C infinity. And these are just inside C infinity of E in that case. So that's not what we mean, really. What we mean is that you can think of D going from, say, M of E of Sobolev space of order m to H0 of E, because it has an extension in that thing, right? Then when you talk about image of D, we mean really image of this map. But this is really L2 now, right? This is L2 of E. But for kernel, it doesn't matter. The kernel, when you consider it among these Sobolev sections, so you allow yourself Sobolev sections to be in the kernel as well, but still they are smooth. This is regularity. So in some sense, this says that generalized solutions of these elliptic PDEs are actually regular functions, or C-infinity functions. Generalized solutions are C-infinity functions because these objects can be very irregular, but they won't because they will be C-infinity. And you have this decomposition. So in this sense, then the result makes sense. So, but then we will prove something to that effect, that also C-infinity of E is also equal to kernel of E plus image of D from C-infinity of E to C-infinity. So there is a corresponding C-infinity decomposition also, but this follows from that. Okay, so there is this issue one has to be aware of. Any questions about the meaning of this statement?
Would this then hold as like almost any Sobolev level?
Yes,
Yeah.
it does indeed. And that's independent of the scale as long as you just choose the difference. Indeed, that's. And for example, it follows that the index calculation is independent of which is equal. Yeah, so that's. So now proof. Okay. Okay. So, by the way, yeah, I just said something, but I better write it. And I said that C-infinity of E is also the sum D of C-infinity of E. So this is also, we can say this is image of D, but D restricted to C-infinite functions now. So the corresponding C-infinity statements holds. So both. So there are three statements here. Right. Okay, so proof. So first of all, this D, of course, we get a bounded function from HS E to HS minus M. E is continuous. For all S, of course, as we know. So since D is elliptic, we can construct the parametrics. There exists a parametrics I don't know what notation, maybe G. G is for green function, for example. Is a parametrics G. Going from HS minus M of E to HS of E, such that GD minus identity is infinitely smoothing, i.e. GD minus identity from HS to HT is continuous for all S and T, in fact. Yeah. But, so we construct this parametrics first. I mean, we know that this exists by pseudo-differential theory. What can we do next? But then we can use a Rayleigh lemma, but HT, HS is compact embedding for all T bigger than S. Okay, so now what we can do, we want to show that this map is compact. So what we can do, we decompose this as products of a bounded map and a compact map. And we know that product of bounded and compact is compact. So then this would be compact on right level. Then I can use Atkinson's theorem that we proved a long time ago to show that actually that operator indeed is spreadable. So that's the idea. So for all T bigger than S, okay. So the idea now is this. So HS to HT going to HS. So this map, this part is GD minus identity. Is compact.
So sorry, GB will go from HS to HS, right?
Sorry?
GB will go from HS to HS, right?
No, but yeah, but I mean, but I'm talking about GD minus identity. This is infinitely smoothing, right? Infinitely smoothing means that from HS to HT, you can define it indeed from HS to HT for all S and T, and that's a bounded operator. Because we have all these Hilbert spaces to map between. This is an embedding. And now I'm going to take this, which goes from HS to HS now. So that's okay. So this is compact. So let me write it as compact. i.e. G minus identity from HS to HS. Is compact. It's a factorization trick, but we had to use the right scale here. I mean, one can use similarly the other way around. One can go the other way around. Similarly, yeah, DG minus identity. Because the way we chose this G was that its symbol, in fact, was the two-sided inverse for the symbol of D in the algebra of pseudo-differential symbol. Modulo infinitely smoothing symbols, of course. It was not an exact inverse, it was modulo. That's why we have these asymptotic notations, but that's fine. Similarly, dg minus identity from HS to HS is compact. So, hence by Atkinson. The map D from HSE HS minus ME is Fredholm. For all S. And that's what you said, Luke. I mean, because you said the result perhaps works for all S. Indeed, it works. So we just establish right now that this map, in fact, from this inverse space to that inverse space is present. You see, this Atkinson's theorem is pure operator theory, Fredholm, abstract Fredholm theory. It's nothing to do with geometry. It's, but it kind of ties up very well with the idea of asymptotic inverse for these pseudos. So that's as far as Fredholmness goes. So then can write. Now we can do this decomposition L2 of E is equal to kernel of D direct sum image of D. But now we have to be, again, like as I said at first, this kernel of D, image of D, everything now is inside L2 of E as maps from, for example, H2 to H0, which would be L2. So this D now goes from H2 to H0. I mean, this is the bounded operator, and it's also self-adjoint. We know that it's self-adjoint, so this decomposition follows immediately. So just pure operator theory at this stage. Okay. So now what is left is to prove the corresponding C infinity of E statement for smooth sections, right? I mean, okay, so first of all, we have to write of this kernel of D star, direct sum image of D in general, but D star is equal to D. So then we get that statement that we wanted. So that's and kernel of D, by the way, is finite dimensional since this D is fertile. That's the definition of one of the conditions for since D is. So yes, so this decomposition indeed is true. So I mean, without, in fact, so I can write it like this. That's what I wrote first. So now regularity. At this stage, I mean, still we don't know that kernel of T is inside C infinity of n. These are generalized solutions. This is inside, H2. These are H2 sections. A priori could be just some functions with maybe 1 times differentiable functions. We don't know if they are infinitely differentiable yet. Because the definition of Fredholm doesn't have any regularity concept in it. Regularity concept comes from differential operators. Abstract Fredholm theory gives us that this is finite dimensional subspace of L2 of E, and we have this decomposition, that's all. On the level of Hilbert spaces, that's all. So regularity, so is Y, in other words, kernel of D is inside C infinity of n. But this was exactly the regularity statement that I proved. I mean, regularity theorem. So do you remember the first version was that if P of U is equal to 0 in some Sobolev space, and P elliptic, of course, implies that U is C infinity. That's the first statement of regularity. And the second regularity result was that if P of U is C infinity, then U must be C infinity itself. And so in general, P of U belongs to C infinity implies that U belongs to C. Okay, but this is enough for this statement. Okay, so this we know that so far that this is inside C infinity of E. That's good. But it could be that this is inside C infinity, but I want to know the decomposition for C infinity of E as this. So Y, so last statement is Y, C infinity of E is actually equal to indeed kernel of D direct sum C infinity of some. Kernel of D direct sum D of C infinity of E. So now let phi be in C infinity of E. Right. So let's take a smooth section. So we can write this as sum of 2 functions by this L2 decomposition. At least we can write phi as equal to phi1 plus d of psi. Well, this phi1 we established that is in the kernel. We are choosing to be in kernel of the. This is C infinity, right? This is also C infinity. So, but this psi originally just a priori is only in Sobolev, right? It's only a kind of Sobolev section. But the difference phi minus phi1 is in C infinity, right? So. D of psi but then the second regularity result shows that the psi itself has to be C infinity. Again, regularity theorem, second part. This is second part. implies that psi itself belongs to symmetry. So we are done. We showed that every smooth section is actually direct sum of some harmonic section plus d of. Okay, so this was very special because we work with self-adjoint operators. But that's enough actually now. So the last step now is we have everything in place to prove Hodge decomposition and everything we want. Any questions before we move? Just need 10 more minutes. Any questions, comments? No questions? Okay. So then let's move on. So then we have this now Hodge decomposition. So this is the theorem, which is Hodge decomposition for elliptic complexes. So so it's a very general context. Let E, which is this one, orientation has always been like this. In an elliptic complex. Then we have orthogonal decompositions. So we have two orthogonal decompositions comparable to what we had. One on the L2 level, the other one on C infinity level. So the one decomposition is that L2 of EI is actually isomorphic. I mean, it's really a direct sum of kernel of delta. Orthogonal direct sum image of E. Orthogonal direct sum image of star. And kernel of delta, so maybe I call it delta I. Kernel of delta I is isomorphic to HI, E are finite dimensional. Also, C infinity of EI is So here, of course, kernel of delta I. So again, another part of the statement is that this is inside C infinity of I. So smooth section, this is the decomposition, and the C infinity decomposition is C infinity of EI is equal to kernel of delta I. Is some D of C infinity of EI minus 1. Takes some D star of C infinity of EI plus 1. So here we have also embedded in this now the wrong theorems, Hodge decomposition. So there are basically two statements packed into this statement. So the finite dimensionality of cohomology groups is a generalization of the wrong theorem, right? So the corollary of this, let me just, before giving the proof, let me give a corollary of this. Apply this general, very, very general statement to the wrong complex. Apply the wrong complex. Which we proved during the tutorial that that's an elliptic complex some time ago. So the Durand complex is this one, 0, omega 0 of n. Really Durand differential d, omega 1 of n. Then omega n of n. Right? So this is, we saw that this is an elliptic complex, so it falls under this general construction. So it follows that, and then you get that, first of all, Durand groups are finite dimensional, right? This is Durand theorem itself, is very valuable. Durand groups, H, Durand, phi of n, which is kernel of t divided by image of d, is finite dimensional. Second, we have Hodge decomposition. I mean, I'm not writing in the right order. I'm just writing three statements. Hodge decomposition holds for differential forms. And third, any Durand cohomology class has a unique harmonic representative. So in other words, we have that kernel. So this is honest to God Laplacian is isomorphic to ith Durand group of A. This is just this statement in this special case. Okay, so but I mean, the thing is, this can be applied to signature complex. This can be applied to Dolbeau complex. This can be applied to a lot of situations, and in each case gives interesting results. So the Durand thing and the Hodge decomposition in this context was the first instance. So this was, I believe, this was first proved by Etienne Singh using the general pseudodifferential or Sobolev space techniques they developed. This concept is actually concept of elliptic complex is a great, great concept. It's a great generalization, and it's due to them, I believe. Yeah, I think it's due to that. And this all goes back to them. So one of the gifts of Etienne Singer and Bott is this result. Okay. So proof of this, I want to give the 5-minute proof before, if it's okay. Is it okay? You're very kind. I know you're tired. Maybe you need a coffee or something. Maybe we should go get a coffee. But maybe we should better finish that because the coffee shop down there is closed. The proof is really easy now, actually. I mean, I can say this. So we are going. So this corollary, of course, is obvious once you have that. But let's just. So proof of this statement. So by previous result, okay, I mean, we can just write any element in the section. What is my notation for sections? Yeah, for any C belonging to L2 of EI, right? We can write this as phi equal to phi tilde. Like something in the image of this Laplacian, right? We just apply the Laplacian complex to this. Plus d star dx sum d star d of some element psi. But this phi tilde belongs to kernel of this. This we know is a smoother. Well, okay, so this belongs. Okay, so this is the L2 decomposition. Well, I mean, this you can write it as, so immediately you see that phi, we can write it as, so what does it say? It says that L2 of E is inside kernel of delta. Not direct sum plus image of delta plus image of D plus image of D star. Look, this is in the image of D. This is in the image of D star. But what we have to do now is to show that these two images are orthogonal to each other, and they're all orthogonal to kernel of D. That's what we have to do. So, but this we do. But image of D is orthogonal to image of this star. Let's see the proof of this. I mean, why is that so? I mean, if you just have D of, say, I don't know, F, for example, and the star of G. So D of F, the star of G. Why this is 0 for all F and G? Well, this is just definition of algebra, right? And it's square 0, so this is equal to F. The star of G, of course, is 0 because this is 0. So the orthogonality of this decomposition follows, and everything just follows from that statement after this. So you have everything. So, I mean, we are done. I mean, there is really nothing left to prove, basically, after that result that we proved about generalized Laplacians. Okay, so, and of course, this statement, one thing we have to, about this also, so let me write it like this, also, kernel of D is equal to kernel, kernel of Laplacian is equal to kernel of D intersection kernel of D star. Remember this, we had this for toy model, we had for baby Hodge decomposition. And in this case, it's also true for formally the same argument. It's just, so this implies that this plus Hodge decomposition implies that the map from kernel of delta I to hi is an isomorphism. Well, first of all, the map is well defined because if something is in the kernel of Laplace and it's closed, so you can push it inside, but then now there are, okay, so we have to do some calculations now, but we'll do it next lecture. But something I want you to pay attention to, namely, the cohomology is independent of choice of metric, right? The drum, so here, so this is essentially done. But here is an important note that H, you see, we use the metric in order to define this. I mean, without choosing Riemannian metric and maybe orientation even, we could not define these harmonic forms. The harmonic forms really depend on choice of metric. This is very important to realize. But these Doron groups are independent of, these are topological invariants, are independent of metric. But harmonic forms I mean, which is kernel of delta I, depends on the choice of metric. I mean, I'm trying to think of a simple example. Of course, if you go to Riemann surfaces, you see it very clearly there. But maybe there are kind of simpler examples. Maybe on the torus I can give, maybe next lecture I can give some examples to show that if you change the metric, space of harmonic sections, harmonic functions, harmonic changes, but its dimension doesn't. It's really a topological invariant. It depends on G, but dimension of kernel of delta I, of course, is the ith Betti number, right? This is the ith Betti number, which is independent of choice of metric. That's one thing we have to realize. What else we should know? Okay, I think it's a great place to stop now. And now we have to see some examples of this. Now this is we are in pretty good shape as far as this part of the analysis is concerned. Of course, as I said, there's going to be another analytic component, which is construction of this heat kernel, which is also interesting. So maybe I stop the video and then we will discuss.